For most of human history, planets around other stars were nothing more than ideas. We knew they should exist, but actually seeing and studying them was almost impossible. Astronomers had to rely on indirect clues. A tiny dip in a star's brightness when a planet crossed in front of it, or a barely detectable wobble caused by the planet's gravity. Those techniques transformed astronomy and revealed thousands of exoplanets. But there was still a major limitation. We could discover these worlds without truly knowing what they were like. That began to change with the James Webb Space Telescope. Webb was designed to observe infrared light, giving astronomers a powerful way to investigate distant planetary systems. Instead of simply asking whether a planet exists, researchers can now begin asking deeper questions. What is its atmosphere made of? How hot is it? Does it have clouds? How does radiation from its star affect its chemistry? One important demonstration came from the direct observation of HIP 65426b, a young gas giant located hundreds of light-years away. The planet is several times more massive than Jupiter and is still relatively young on a cosmic timescale. Because it remains warm from the energy left over from its formation, the planet produces detectable infrared radiation. Webb was able to capture this faint emission, producing an important demonstration of its ability to directly image distant planets. The resulting image may look like little more than a tiny point of light, but scientifically it represents something much bigger. Astronomers were able to separate the planet from the overwhelming brightness of its host star and study it as an independent object. And this is where the story becomes even more interesting. Webb isn't limited to photographing planets. One of its greatest strengths is analyzing their atmospheres. Consider K218b, a planet located roughly 120 light-years from Earth. It is significantly larger and more massive than our planet and orbits a cool red dwarf star. Because of its location, scientists have investigated whether its environment could potentially contain conditions compatible with liquid water. But K218b is not simply another Earth. When the planet passes between its star and Webb, some starlight travels through its atmosphere before reaching the telescope. Different molecules absorb different wavelengths, leaving patterns in the light that researchers can analyze. This technique is called transmission spectroscopy. Webb observations have provided evidence for molecules including methane and carbon dioxide in the planet's atmosphere. There have also been intriguing discussions about possible dimethyl sulfide, or DMS, but that interpretation remains uncertain and requires additional observations. That distinction is extremely important. A potentially interesting chemical signal is not automatically evidence of life. On Earth, DMS is strongly associated with biological activity, particularly marine ecosystems, but scientists cannot simply assume the same conclusion applies to another planet. There could be unknown chemical pathways capable of producing similar molecules without biology. K218b therefore remains an intriguing scientific puzzle rather than a confirmed inhabited world. And that uncertainty is actually one of Webb's greatest contributions. The telescope allows scientists to move beyond dramatic speculation and examine distant planets through measurable physical evidence. Another world has provided an entirely different lesson. WASP-39b is a hot gas giant orbiting extremely close to its star. Its atmosphere reaches temperatures far beyond anything comfortable for life, yet it has become an extraordinarily useful laboratory for studying atmospheric chemistry. Webb detected several important molecules in its atmosphere, including water vapor, carbon dioxide, carbon monoxide, sodium, potassium, and sulfur dioxide. The sulfur dioxide detection was particularly significant because it provided evidence of photochemical processes occurring high in the atmosphere. Powerful ultraviolet radiation from the host star interacts with atmospheric molecules, driving chemical reactions that transform the composition of the planet's upper atmosphere. This demonstrates that an exoplanet atmosphere is not a static shell surrounding a world. It is a constantly changing environment. Radiation, temperature, atmospheric circulation, and chemistry interact continuously, creating conditions that may be completely different from anything found on Earth. And Webb is allowing astronomers to study these processes from across interstellar distances. But the biggest question remains. Could one of these distant worlds actually support life? To approach that question, scientists need to examine planets that are smaller, cooler, and potentially rocky. That brings us to one of the most famous planetary systems ever discovered, TRAPPIST-1. Its 7 roughly Earth-sized planets orbit a small red dwarf star, with several positioned in or near the region where temperatures could potentially allow liquid water under suitable conditions. The discoveries made by the James Webb Space Telescope are changing one of astronomy's biggest questions. For decades, the search for life beyond Earth was dominated by a simple idea: find planets similar to our own. Scientists searched for worlds roughly the size of Earth, orbiting at distances where temperatures might allow liquid water. But Webb is showing that the story is much more complicated. A planet can be in the habitable zone and still have no atmosphere. A planet can contain water-related chemistry while possessing an environment completely unlike Earth. And a planet can be covered by a massive atmosphere whose chemistry is driven by radiation from its star. These differences are not disappointments. They are clues. Every unusual world helps scientists understand the enormous variety of planetary environments across the galaxy. One of the most important breakthroughs is that Webb can study atmospheric chemistry with remarkable sensitivity. When a planet passes in front of its star, its atmosphere leaves a chemical fingerprint in the starlight. Scientists can separate that signal from the much brighter light of the star and search for evidence of particular molecules. The process is extraordinarily difficult because the planetary signal can be tiny. Yet with repeated observations, researchers can build increasingly detailed models of distant atmospheres. This is why worlds such as K218b are so important. The planet has generated considerable interest because observations have revealed carbon-bearing molecules and other atmospheric features. But scientists remain cautious about interpreting those results. A molecule associated with life on Earth does not automatically prove that life exists elsewhere. This is one of the most important lessons from modern exoplanet research. The discovery of a potential biosignature would need to survive extensive testing. Researchers would need to determine whether the signal is real, whether the molecule is actually present, and whether geological or photochemical processes could create it without biology. Only after eliminating plausible non-biological explanations could scientists begin discussing a biological interpretation with confidence. That careful process may sound slow, but it is essential. Extraordinary claims require extraordinary evidence. Webb's observations of WASP-39b demonstrate the same principle from another direction. The planet is clearly hostile to Earth-like life, yet its atmosphere provides a natural laboratory for understanding planetary chemistry. The detection of sulfur dioxide revealed how stellar ultraviolet radiation can drive chemical reactions in an exoplanet atmosphere. This means astronomers are no longer simply cataloging planets. They are studying weather, chemistry, radiation, clouds, and atmospheric evolution on worlds that are hundreds of light-years away. And as Webb continues observing, the focus will increasingly shift toward smaller planets. Rocky worlds are much harder to study than giant gas planets because their atmospheres produce weaker signals. Their stars can also overwhelm the tiny amount of light passing through the atmosphere. But technological advances and repeated observations may eventually allow astronomers to examine the atmospheres of potentially habitable rocky planets in much greater detail. The TRAPPIST-1 system remains one of the most fascinating targets for this reason. 7 Earth-sized planets orbit the same star, creating a natural laboratory for comparing different planetary environments within one system. If some of those planets retain atmospheres while others lose them, scientists can investigate why. Perhaps stellar radiation stripped an atmosphere away. Perhaps the planet's magnetic field played a role. Perhaps geological activity replenished gases. Or perhaps the planets formed under completely different conditions despite being located in the same system. These questions matter because Earth's habitability may depend on a rare combination of circumstances. Liquid water alone may not be enough. A planet may also need an atmosphere capable of surviving stellar radiation, stable environmental conditions, suitable chemistry, and perhaps geological processes that regulate its climate over enormous periods of time. Webb is helping scientists investigate these possibilities one world at a time. And there is an important reality behind all of this. The James Webb Space Telescope has not confirmed extraterrestrial life. It has not discovered a second Earth. It has not proven that K218b is inhabited. Instead, it has accomplished something arguably more valuable. It has given humanity better tools for asking the question scientifically. We can now examine distant atmospheres, identify molecules, measure temperatures, investigate chemical reactions, and compare planetary environments across the galaxy. Every observation narrows the possibilities. Every spectrum provides another piece of the puzzle. And eventually, perhaps, Webb or a future telescope will examine a rocky planet whose atmosphere contains a combination of gases that cannot easily be explained by geology or ordinary chemistry. That would be a very different kind of discovery. For now, however, the evidence tells us something already extraordinary.